of the transport fate and the effect of pollutants on our health and environment. So that's why the third block is on pollution chemistry. We will discuss day after tomorrow, so which is on I think 11th. 11th we will discuss pollution chemistry. It has 4 units: 8, 9, 10, 11. 8 unit 8 chemistry of air pollution 1, unit 9 chemistry of air pollution 2, unit 10 parameters of water pollution, unit 11 chemistry of hazardous substances, hazard and wastes. And block 4 is analytical techniques in environmental chemistry. So in block 4, analytical techniques in environmental chemistry that we will discuss, which is on 12th, we will discuss. And it has 4 units: basic analytical techniques, spectrometry, and chromatography. Unit 14 is chromatography technique. Unit 15 is radiochemical techniques. With this, we will end the environmental chemistry syllabus. So today, let us start the block 1, which is on fundamentals of environmental chemistry, and in that we will discuss what are the syllabus. What are unit 1? We will discuss environmental chemistry 1. In environmental chemistry 1, what are the subjects we are going to discuss? First, we will discuss concept and scope of environmental chemistry, fundamentals of elemental stoichiometry. Am I audible to all of you?
Yes, sir.
Yes, sir.
Okay. So you may call your friends to join. Those who haven't joined and the class, tell them to join online, and they might have the you can forward this link, the link that you have joined. You can forward in your group link, group WhatsApp group. In group WhatsApp, you can share this link to them so that they can join. They all can join. Okay. So let us first discuss about introduction. Introduction. Environmental chemistry is traditionally outlined as the study of the origin, roots, reactions, impacts, transport, and fortunes of chemical species in water, soil, and air environment, and the human activity influence on these. So basically, environmental chemistry is outlined by the study of the origin, roots, reactions, impacts, transport, and fortunes of chemical species in water, soil, and air environment, and the human activity influence on these. So according to this definition, the environmental chemistry is generally focusing on pollutants in the various environments. So basically, our aim is to focus on the pollutants. Which kind of pollutants? They pollute air, water, and soil basically, and their fate, transport, and their they and their effect on human health. Okay, so then this updated definition: the study of chemical balance in natural systems and how the disturbance in this chemical balance happens by the anthropogenic activities. Anthropogenic activities mean human activities, by releasing of chemicals into the environment which change the natural ecosystem level. So basically, how human activities or anthropogenic activities they destroy the environment and change the natural ecosystems, and by altering the chemical balance in the natural system. So that will be discussed, that will be discussed in this environmental chemistry, and that is also the definition of the environmental chemistry. So scope is basically there is another term called green chemistry also, but it should not be synonymous of green chemistry. Green chemistry is different. Green chemistry aim to implement chemical process that uses smaller amount of harmless chemicals. So basically, green chemistry is basically we are going to design a pathway in the chemistry the subject to reduce environmental pollution. So what environmental chemistry is, we should is to understand the chemical reaction and processes that regulate the environmental systems and how the introduction of anthropogenic chemicals affect them. So there is a fundamental difference between green chemistry and and so let them forward them. Please forward them the link in the in your WhatsApp group. Then they will join. So basically, everything that happens in the world around us could come under general heading environmental chemistry. So what is environmental chemistry? Anything happening in our environment. So basically we stay in the environment. We have on the head, our head is air, our we are walking on the soil and we are drinking water. So water, air and soil, we are associated with them. So anything happening in this world is can be classified as environmental chemistry if some kind of chemical or some kind of chemistry involves in that. Okay, so the topics that are rather distance from the equations and reactions should be also discussed. Basically, knowledge in biological, meteorological, oceanographic, and other fields, conservation of environmental resources along with biological diversity, pollution prevention, social problems associated with growth and environment, design of renewable energy network that is not polluting. Everybody, whatever profession is impacted by environmental problems such as global warming, ozone depletion, declining of forest energy resources. So these are all means like these all of these things collectively can be classified as environmental chemistry. Nutrients and organometallic compounds, environmental protection, and sustainability, sustainable environmental law, business administration, all those things. So fundamentals of environmental stoichiometry. So stoichiometry, what is stoichiometry? Anybody has idea about stoichiometry? Stoichiometry is basically a chemical reaction written in the form of equation. So when you write a equation, chemical equation in the form of equation, chemical reaction in the form of equation, the idea of both qualitative and quantitative features, where qualitative is more a theoretical approach, but quantitative is explicitly a practical and more and approach summarizing basic principles of chemistry. So basically, see this is methane plus oxygen, carbon dioxide plus water. So but this is not balanced equation. If you balance it, you have to incorporate a 2 here. One molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. So this is a balanced equation. So if a equation is written and not balanced, there is no meaning of that reaction. So we require to poets the so what happens is in equation the reaction describes the formation of carbon dioxide and water from methane via combustion process. The reaction describes the formation of carbon dioxide and water from methane via the combustion process, but the quantity of elements in the reactant side and the product side are not equal. So hence it requires to poise the element proportion on the either side to determine the amount of each compound involved, which is defined as stoichiometry. So for example, if you don't write 2 oxygen here, but it will not fulfill the stoichiometry, because it doesn't specify how many number of molecules or how much amount of oxygen required to burn the methane to carbon dioxide and water, and how many molecules of water molecule is also generated. That is also important. So stoichiometrically balanced equation can be achieved by a trial and error approach. So you have to do a trial and error. That means first time you see one water, if it is not working, first time you take one oxygen, if it is not working, take two oxygen, and then if it not if how many molecules of water is coming out, one molecule is coming out, then if it's not working, multiply it two to make it balanced equation. Okay, so stoichiometrically balanced equation can be achieved by a trial and error approach, one carbon approach on both sides of the equation, but on the left side there are four hydrogens. So there how you just read this how it has been balanced. So basically you have to do a trial and error. First oxygen, it is not completely fulfill or burn the methane molecule to carbon dioxide. If you take two more molecules of oxygen, then only it will give you one molecule of carbon dioxide and two elimination of two water molecules. So this is how you can do the chemical equilibrium. You know, chemical equilibrium. Chemical equilibrium means is defined as a reaction a reaction is in chemical equilibrium if the forward reaction rate step equivalent to the reverse reaction rate step. So equilibrium means so there are two steps, forward and backward reaction. So if the forward reaction step is equivalent to the reverse reaction step, so that can be called as the reaction exists in equilibrium. So if you add carbon dioxide and to water, and it will dissolve, carbon dioxide will dissolve and you get carbonic acid H2CO3. Without the chemical equilibrium, so there is a see two arrows here, front arrow and back arrow. So if both the systems, carbon dioxide and water, when they are dissolved and then the carbonic acid produced, both are in equilibrium with each other. So that means whatever occurring in the forward step is equivalent balanced by a reverse step. Okay, so without the chemical equilibrium it would not be possible to exist as you know it. So another sign of equilibrium in our daily lives occurs within our own bodies. Hemoglobin is a macromolecule which carries oxygen to all of our bodies. So you know where is hemoglobin is present in our blood. What is the role of the hemoglobin? What it does, hemoglobin? What does hemoglobin? What it does? Any idea? Am I audible to all of you or not?
Yes, sir.
Hemoglobin carries oxygen in our blood and it transfers the oxygen to our tissues. Okay, so all over the body. So what happens is when the blood gets saturated with oxygen, that means enough oxygen is there that binds with hemoglobin. It passes through the blood and it goes to the tissues, where tissues require oxygen for their survival and oxidation process. And when the oxygen is delivered to our tissues from the hemoglobin, then oxygen is gone, again hemoglobin becomes free, again it returns via blood to the lungs, and when it passes through the lungs it again enriched with oxygen, and again it goes back to the tissue. So this is basically see here how the iron is there and hemoglobin, this is the hemoglobin. So hemoglobin requires 4 oxygen molecules. So one hemoglobin acquires 4 gram of oxygen, so it becomes oxyhemoglobin. That means one oxygen hemoglobin molecule can bind with 4 oxygen molecules to form oxyhemoglobin. Hemoglobin binds with oxygen. This is also a equilibrium process. So both binding and detachment of hemoglobin, oxygen from the hemoglobin is a reversible process. Another open system and closed system. Open system means you are taking a beaker without a cover. If you cover it, it becomes a closed system. And if you keep the water inside the closed system, then there is a possibility of condensation. Condensation will occur, and then when the water will evaporate, it will condense in the surface of the of the of the of the cover. Okay, so in that cover, and then it will come back again to the liquid water as liquidator. So this is a process that will continue. So that is a basically a closed system. And so then next is reversible reactions. There are certain reactions which can occur in two directions. First direction is forward direction. Already I told you, reversible irreversible reaction. Forward reaction, first direction is forward reaction, in which the reactant come together to save the products, while in other direction so x plus xy plus z, forward direction x plus yz, reverse direction xy plus z. In reversible reaction, another example is hydrogen plus iodine 2Hi. So this is a forward reaction. The forward reaction always written in left to right from the reaction. So 2Hi gives you H2 plus I2 is the reverse reaction. The reverse reaction always written right to left of the given equation. So this is the rate of reaction and time is there. So there is a equilibrium process is there. So that means when both the forward reaction and reverse reaction, they come their rate, they are equal with each other. So that is called equilibrium point. Okay. So although no macroscopic changes can always be detected, this does not mean the reaction has ended. The forward and reverse reaction tend to occur, and so there are still macroscopic changes in the system. So this state is called dynamic equilibrium. When always there is a forward backward reaction continues, it's called dynamic equilibrium. Reaction which are going to be completed are irreversible. Reaction if a reaction is going to complete it, so that is reversible reaction. That means it will not it will not have a dynamic equilibrium. There will be no forward reaction, backward reaction, only one way reaction. Reaction starts and ends, and then product forms. So that is the end of it. So these are called irreversible reaction. So next is chemical potential. In the year 1875, Gibbs coined the word chemical potential. What is chemical potential? Chemical potential is the concept of thermodynamics. In thermodynamics, there is a post called chemical potential, common to all. Not all in the study of materials, but also in physical, chemical engineering, and biological background, biology background also. So the key concept is that it is possible to achieve all the thermodynamically impressions of a substance at a given temperature and pressure from knowledge of its chemical potential. So chemical potential establishes the stability of materials under the constant pressure and temperature. So chemical potential, there is a stability of material under constant pressure and temperature, such as chemical products and solutions, and their capacity to react chemically to form new materials, to turn into another physical state, or to move from one space position to another. So there are few important points related to chemical potential, such as chemical potential energy mainly depend upon the strength of the bonds. Strong bonds have low energy and weak ones have high energy. So chemical potential, potential energy mainly depends upon strength of the bonds. So where the chemical potential energy comes from? It's coming from the breaking or making of the bond process. Okay, if a bond breaks or a bond is formed, strong bonds have low energy and weak one have high energy. If a bond is very strong, they have low energy, and if the bond is weak, then they have high energy. Large quantities of heat and light energy can be released during strong bonds are forming. So when in other terms, chemical potential is correlated with the system's electronegativity. So electronegativity means, electronegativity, some elements like oxygen, fluorine, chlorine, halogens, they have the capacity to draw the electron towards themselves. So that potential is called electronegativity. So the relationship between chemical potential and electronegativity equal to mu. Mu is a chemical potential equal to psi into which in minus 1. So where psi is electronegativity. So the stored energy in the food molecule are preserved in the form of chemical potential energy. So for example, we are eating rice, so that rice has some stored energy in it, so in the form of chemical potential energy, which goes into our body, and we survive with that, we get energy out of it. So that is called chemical potential energy, which is stored in the food molecules. Okay, our body breaks the molecules for catabolism and release energy, can be used for work. So this is value of chemical potential of a substance depends upon both temperature and pressure. So the chemical potential depends upon pressure and temperature. Additionally, the potential will increase when the pressure increases. Intensive properties are substance dependent and depend entirely on the material. So basically, depends upon the material. Some intensive properties like chemical potential, temperature, density, refractory index, all those. Chemical energy is the capability of the chemical to undergo a chemical reaction to turn it into other substances. Example include food, batteries, fuel, etc. So when the chemical reaction occurs and it undergo a particular chemical particular so they give energy. Breaking or creating chemical bonds require energy which may be either evolved or absorbed from chemical system. Chemical energy is a type of potential energy. So chemical energy is what? Is type of potential energy. However, kinetic energy is the energy of motion. If a body is in motion, for example, a bus is moving, so you are standing on the bus and suddenly bus stops, so you go forward, you leap forward. So that is because of the kinetic energy that you gained when the bus is moving. Suddenly, if it stops, then you might fall down. So that is because of kinetic energy. But this chemical energy is a potential energy which is inside the substance, which is releases because of the chemical reaction or chemical burning of a substance or chemically breakdown in our body. We eat some food and it breaks down in our body and provides energy. So that is breaking down of process. So this is called potential. So then what is kinetic? Chemical kinetics. So what is chemical kinetics? Chemical kinetics is another term. Chemical kinetics is the evaluation of rates, is the evaluation of the rates and mechanisms of chemical process. This is of great practical importance. So chemical kinetics is also how fast a reaction will occur or how slow a reaction will occur, so and the mechanism of their reaction. So that processes are called chemical kinetics. This is it is also important to know under what condition a slow but valuable reaction can be made to proceed rapidly to produce a desired high yield product. So for environmental chemistry, it has great predictive value. So by observing the kinetic and environmental reaction mechanisms, we can at least estimate approximately the residence time of both polluting and non-polluting organisms. So basically, how long a reaction will occur, how long a chemical will be in the environment, all these can be found out by observing the chemical kinetics of the reaction of the particular reaction. Our knowledge of various pollutants and atmospheric phenomena such as depletion of ozone, acid rain, photochemical smog is focused primarily on the study of kinetics of individual rate constants of thermal and photochemical reaction. Understood? Any problem? Any problem?
No, sir.
So am I audible to all of you, or you won't hear me?
Yes, sir.
Okay, so let us discuss about kinetics of reactions of different orders. So at zero order reaction, what is a zero order? zero order reaction occurs at a constant rate and the magnitude of rate does not change with time. So what is zero order reaction? It occurs at a constant rate and the magnitude of rate doesn't change with time. So the concentration plot against time is linear. So when you plot concentration versus time, it is linear and the slope of this line is equal to zero order rate constant. So differential rate equation for zero order reaction, d minus dA by dt equal to k, which is equal to x into t. So what is k? Is the first order rate constant. dA by dt, that means rate of change of reactant A. A is the reactant. So square bracket of A means concentration of A, where K is the zero order rate constant and X is the amount reacted in time t. For fast order reaction, there is the rate depends upon fast power on the fast power react concentration. First, the rate of the first order reaction. So then, what is the first order reaction? First order reaction is the rate depends upon fast power reactant concentration. So it's a fast power. So that means what is the rate equation? Minus dA by dt equal to k into a. K is the first order rate constant, and dA by dt is the change of the concentration of reactant A with time. Okay, so on integrating this equation 3, so this equation 3 can be integrated to obtain log a0 by a at time t equal to 2.303 kt, or a into t equal to a into e to the power minus kt, or log a by a minus x equal to 2.303 into kt, where a0 is the initial concentration of the reactant and at is the concentration at time t equal to a minus x. The concentration of reacted in time in t time equal to x. The unit of first order rate constant equal to second inverse. So the zero order rate reaction, it doesn't have any rate constant, the unit, but here the unit of first order rate constant is S inverse or second inverse. It is independent of the unit of concentration used. Second order reaction, in one of which in one or in one which the rate depends upon the concentration of one reactant raised to power 2. So basically power 2. So a square, you see a to the power a square, rate proportional to k into a to the power 2. This is the rate is 2, or rate equal to proportional to k, rate equal to k, which is the second order rate constant, into the concentration of reactant A and B. If there are two reactants are there, if you combine together, that also, or if one reactant is there, its rate equal to second order rate constant into square root of the concentration of A. So basically power, if power equal to 1, this power equal to 1, this is called first order. If power equal to 0, then it is called zero order. So this is basically power, depending on how much power is there. So here if you integrate that, you get k equal to 1 by concentration of A at time t minus 1 divided by concentration of A at time 0. Okay, so this equation 7, what is with this equation 7, the symbols have meaning in the case of first order reaction. The unit of a second order reaction is liter mole inverse second inverse, L mole inverse second inverse. Third order, so that we see here A to the power Q. So concentration of reactant A to the power 3. So that's why it's a third order reaction. But if there are two reactants are there, A is there, B is there. So if either A square or B square. If A is there, it should be B square. So rate equal to constant K into A into B into C. So all three are there. That will be A into B into C. Under the condition A, concentration A of A equal to concentration of B equal to concentration of C. So the rate laws will also reduce the rate of the equation. So that if it is a third order reaction, the rate constant K you can be derived from this equation. Okay, so atmospheric oxidation of nitrous acid by oxygen 2HNO2 plus O2 equal to 2HNO3 obeys the third order rate law. So minus dO2 by dt equal to K HNO2 into O2 square. So the unit of third order rate constant equal to L square mole in mole to the power minus 2 second inverse. Pseudo order reaction, because of the experimental conditions used, the order of chemical reaction tends to be less than true order. Basically, pseudo order reaction arises when there is a significant excess of one or two reactants relative to the other. If the concentration of one reactant is very high compared to the concentration of other reactant, so that case it is called pseudo order reaction. For example, you add lot of water to a reaction. So that if you add too much of water, then it will be water is the concentration of water is too high. So that means in respect to the other reactant. So then this is called, in that case it is called as pseudo order, because one of the reactants in the reaction has a very high concentration compared to the other. For example, atmospheric reaction NO plus O3 becomes NO2 plus O2. Obeyed the rate law, dO2 by dt equal to K NO2 into ozone. Under the condition O3 in large excess greater than 10 times of the nitrogen monoxide NO. So up to the end of the reaction, there will be hardly any significant change in the ozone concentration. So the ozone would remain virtually constant. So this becomes, in this case K1 equal to K into concentration of NO. So the apparent order in O3 will obey, reaction will be zero order. So the reaction will therefore follow the first order kinetics. So that means the order of O3, for O3 it will be 0, and for NO it will be first order reaction. Simple reaction mechanisms. So basically, the transformation of organic chemicals most often occur in several molecular events referred to as elementary reactions. So when a organic chemical is there and there is a reaction occurs, so basically the events referred to as elementary reaction. An elementary reaction is described as a process. What is elementary reaction? It is a process in which reacting chemical species pass via a single transition state without the intervention of an intermediate. A sequence of individual elementary reaction steps constitutes a reaction mechanism. So basically, sequence of individual elementary reaction steps, step 1, step 2, so that constitutes the reaction mechanism. For example, the overall reaction of hydrolysis of Gibbs base. So this is the amine is there, secondary amine. When water is treated with that, hydrolysis will occur and you get ketone plus amine. So this process is overall reaction is a hydrolysis of Gibbs base. So the reaction mechanism for this seemingly simple reaction is in fact quite complex and it's composed of 4 elementary reactions. So see, there are 4 steps. First step, hydrolysis occurs in the presence of hydrogen. So protonation of nitro group here. Second, water reacts with the protonated nitrogen like this. Third, hydroxyl group is there that takes away the hydrogen from there. So fourth, what happens is you get the ketone plus amine. So the reaction occurs in 4 steps. 4 steps. So that means the mechanism of the reaction involves 4 steps. After 4 steps, you get your desired product, which is ketone and amine, is the byproduct. So a reaction mechanism, order and molecularity of a chemical reaction. Reaction order. So we already discussed the power to which it is raised. So if K into A square or A cube, so that is called reaction order. What is the definition of that? The reaction order relating to a chemical species is defined as the order of a concentration in the differential form of the reactant species of the rate law, and the order of a reaction is defined as sum of the powers of all the concentration terms that occurs in such a rate law. So basically, you see one example: 2NO2 plus O2 equal to 2NO2 gives you 2NO2. So dO2 by dt equal to K. K is the rate constant. NO to the power 2, NO concentration to the power 2, and O2 concentration. So in this case, there is a 2 here over NO, power is 2, and here oxygen power is 1. So this shows the order is with respect to NO is 2 and with respect to O2 is 1. So the order of the reaction would be 2 plus 1 equal to 3. So basically all the reactant, what is the power of the reactant concentration here? If there are two reactants, one is 2 and other is O2, so that is 3. Okay, so consider, so molecularity of a reaction. Reactions typically occur in more than one step. So reaction typically occur in more than one step. Is it audible and visible?
Yes, sir.
Yes, sir.
Okay, so molecularity of a reaction. Reaction typically occur in more than one step. So each reaction is comprised of a series of elementary reactions. So the molecularity is the number of reactant molecules, ions, radicals, or any other chemical species in an elementary step. A reaction may have two or more steps. So unimolecular reaction require only one molecule of the reactant. So for example, O3, one molecule here with ozone, and HNO breaks down to oxygen plus O2. So this is how the ozone depletion of ozone layer. Bimolecular reaction involves two reactants. So one reactant here and another reactant here, both combined together. So bi. Trimolecular, three molecules. So next is chemical reactions. There are several chemical reactions involved in environment. Among them, so that there are different type of, one is hydrolysis. Hydrolysis is an example of a nucleophilic displacement reaction in which a nucleophile attacks the electrophilic atom. So here you see, so basically reaction of water, hydrolytic processes are not limited to the bodies of water such as rivers, streams, lakes, and oceans, usually associated with the term of aquatic ecosystem. Hydrolysis of organic chemicals or chemicals also can occur in fog water, biological systems, ground systems. So basically hydrolysis process means a reaction in which water reacts with a particular reactant to produce to produce so see here water, so you have a elimination reaction. So so that is, so in these reactions there are, you see in this place here you see there are different halogenation of elimination. So then your nucleophilic substitution, then your so many different type of your hydrolysis reactions are there. So that means any reaction where either a hydroxyl ion, OH minus ion is there, when water dissociates it produces H plus and OH minus ion. So any of these processes where a water molecule is involved in the reaction is called hydrolysis. So here you see Rx is a plus H2O gives you ROH plus X minus H plus. So reduction, reducing reducing environments. So what is that? That means if a in a process, if you what is the source of electrons is natural environments. So basically there is a rule: if there is a gain of electron, then it is called reduction, and if there is a loss of electron, that is called oxidation. GER, gain of electron, reduction. GER, LEO, loss of electron, oxidation. So that means any reaction where there is a reduction is occurring, that means the reactant is gaining electron. So there are many different type of reduction reaction: reductive dehalogenation, nitroaromatic reduction. So the examples of reductive reactions are there here. So many there are examples are there. Third is so next, oxidation. Oxidation, as I told, Loss of electron is oxidation. Gain of electron is reduction. So basically, any reaction where either gain of electron, loss of electron is there, or gain of oxygen or loss of hydrogen, that is called oxidation. And reduction process, gain of hydrogen or gain of electrons is called, if you add hydrogen to that, that is called reduction. Oxidation here. So basically, examples, when there are many approaches how we can do the oxidation. If a molecular, you take molecular oxygen, auto oxidation will occur. Hydrogen peroxide also you can involves as a oxygen donor. Hydrogen peroxide is oxidizing agent. So and you take surface reactions like clay, silica oxide, silicon oxide, aluminum oxide at the surface. They absorb the chemicals, and that also gives you thermal oxidation. That also reactions with disinfectants. Water disinfectants have been quite successful in practically eliminating many acute waterborne diseases from the countries where it has been widely practiced. But its possible role in the development of chronic health disorders such as cancer have not been fully scrutinized. Potential biohazards arise during drinking water treatment, and disinfecting agents are used for treatment of industrial waters. So environmental photochemistry. Photochemistry is what? The uptake of light energy or quanta of energy. So your light has photons. So if that photons is absorbed by particular substance for the reaction to occur, so that kind of chemistry, or that kind of phenomena is called photochemistry. Basically, light energy from the photons or light is absorbed by the reactants of a particular reaction to produce the products. So that is called photochemistry. So you see, internal conversion is there. So in photochemistry, you have so many processes that involves the absorption of the energy. For example, internal conversion, fluorescence, intersystem crossing. So all these things. And another important thing is quantum yield. What is quantum yield? The quantum yield of any photochemically induced process is defined as that fraction of the species converted to an excited state that undergoes a fate. So basically, so after light is absorbed, what is the fraction of the particular species converted to an excited state or goes to excited state? So or undergoes a particular reaction, or undergoes a change in color. So that is called quantum yield. Conversion of a triplet to corresponding ground state singlet is another quantum mechanically forbidden and usually inefficient system crossing process known as phosphorescence. Okay, so basically phosphorescence is there where intersystem crossing is there, that is called phosphorescence. Okay, and fluorescence is there. Fluorescence is basically when you apply UV light, it absorbs, the molecule absorbs it, and then it irradiates back a different in the different range of the visible spectrum, or different part of the visible spectrum, that is called fluorescence. So you see, and then there is another chemical reactions involved. So there is another reaction, it's called Diels-Alder reaction. Diels-Alder reaction, a classic synthetic organic chemistry reaction, is theoretically a 4+2 cycloaddition in which a diene and a dienophile with very different electron abundances combine to form a new 6-membered ring. The reaction has great synthetic usefulness and has attracted many researchers interested in its practical application and mechanistic aspects. So a diene reacts with dienophile. Diene means a two pi bonds or double bonds conjugated with each other with a carbon-carbon single bond. And dienophile is a double bond to which a electron withdrawing group is attached. So that is dienophile. So they combine together to form that. So next is catalysis. Catalysis is, you see, catalyst is used to reduce the activation energy of a reaction. So if a, see this figure shows a reaction without catalyst and which has very high activation energy, but if you add little bit of catalyst, it will reduce its activation energy, and you get the activation is very small activation energy is required for that. Okay, so catalysis is a process where a very little quantity of foreign material, so basically where a very little quantity of foreign material called a catalyst raises a chemical reaction rate without being absorbed by itself. So basically it raises the rate of the reaction. The reaction, if a reaction without any catalyst can occur in 10 hours, if you add a catalyst to that reaction, it may occur in 1 hour. That means your 10 hour, 9 hour of your reaction is saved, time is saved, and that energy is saved, and also the reaction becomes faster. So this is called catalysis. So there are two types of catalysis: homogeneous catalysis, catalyst and reactants in the same physical state; heterogeneous catalyst. That means if your, what is a system at homogeneous catalysis? So that means if both are in liquid, so your catalyst and your substrate or the reactant, if both are soluble in water or any solvent, so and the reaction occurs in that stage inside the solvent, that is called homogeneous catalysis. Heterogeneous catalyst means a catalyst, a reaction occurs over a particular support, solid support. Both are in different phase. So that means if a catalyst in solid phase, a reactant or the in a different phase, liquid phase. So types of catalysts, there are various types of catalysts, but usually there are four types. So positive catalyst, negative catalyst, auto catalyst, induced catalyst. There are four types of catalyst. So surface catalyst, surface and aqueous catalysis, clay catalyzed reaction or rearrangement. So basically in the surface of a particular adsorbent like a clay or silica gel or your charcoal. So this is a adsorbent on which the reactant is adsorbed, and on the surface of the adsorbent the reaction occurs. So that is called. So then adsorption in catalysis. Adsorption means, basically a process, a physical process in which a particular silica, activated charcoal, alumina, silicon dioxide, bagasse, zeolite, bentonite clay. So all these are basically adsorbents. So that means, so they absorb the particular substance because they have porous surface, and they have porous means pores are there, small tiny pores are there, and very high surface area, and they absorb either a gas or a liquid or a solid molecule onto their surface. So for the reaction to occur. So classification of adsorbents. Adsorbents are categorized into non-polar solids, polar solids, chemical adsorbing surfaces. So all these. Adsorbents can also be classified as conventional and non-conventional adsorbents. Activated carbon, polymeric carbon, aluminous, silica gel, bauxite, etc. categorized as conventional adsorbent, while in non-conventional adsorbents include hardwood, lignite, fly ash, sawdust, all these. Okay, so basically Okay, so basically, polar solids and non-polar solids, chemical adsorbing surfaces are there. So, and adsorbent can also be classified as conventional or non-conventional adsorbents, activated carbon, polymeric carbon, aluminous, silica gel, bauxite, etc. categorized as convention adsorbents, while in non-conventional adsorbents include hardwood, lignite, fly ash, sawdust. So, so how the factors affecting adsorption. So there are some of the significant variable affecting adsorption are nature of adsorbent and adsorbent, diffusion through the passage within the catalyst particles, surface area of adsorbent, activation of adsorbent, rate of airflow, vapor concentration, humidity, temperature, degree of regeneration, contact time, processing method adopted, etc. So the slowest of all these three steps will determine the rate of the whole process, and uh, is called rate determining step. So basically, it can be what are the isotherms of adsorption on which the adsorption process is governed. It could be Henry's, Langmuir, Henley's, Temkin, Flory Huggins, Ilovich. So there are 5 6 isotherms on which that governs the adsorption phenomena. So you can go through them. We have very short period of time to complete it. So now we will go to the next unit 2. In unit 2, which is environment chemistry 2, here we have what are the things are there: objectives, acid base reaction, ionic product of water, pH and POH, hydrolysis, buffer solutions, common ion effect, oxidation and reduction. So all these. Okay, so let us first discuss acid base reactions. What is acid base reaction? Am I audible to all of you?
Yes, sir.
Yes, sir, audible.
Okay, so now let us discuss about acid base reaction. When an acid reacts with a base, a salt and water is produced. What is the acid? Hydrochloric acid, nitric acid, that can donate a hydrogen ion, H plus ion. So here, so then, and base is basically which can generate a hydroxyl ion. Okay, so when they react together, basically acid donates proton and base donates a hydroxyl ion. So then what will happen? So then basically then what will happen? So when acid and base they react together, another acid, another base is produced. Basically a conjugate base, S acid and conjugate base is produced. So that then another thing is, or a salt and water is also produced as in so yes, Na plus NaOH plus HCl, NaCl plus water. So that gives you Lewis concept. In another definition of acid and bases was introduced by Lewis, G.N. Lewis, based on his investigations. He revealed that both acids and bases are capable of forming a covalent bond. During this phenomenon, an acid accepts a pair of electrons, whereas base donates it. So basically, see, when a acid means which can donate a pair of electron and a base accept a pair of electron. So this BF3 plus NH3. So this is how acid and NH3 is a base. BF3 has electron, it can donate. A nitrogen has vacant orbital, p orbital, it can accept a pair of electron. So adduct will form acid base, Lewis acid and Lewis base concept. So this you can go through. Acid base equilibria in water. So for example, acetic acid is a weak acid. When it dissolves in water, then H3O plus is produced and acetate ion is produced. So in conventional manner, the above can be written as CH3COOH, which this equilibrates with H plus and CH3COO minus. So then you have then the K is the equilibrium constant, the concentration, which is the concentration of these two, multiplication of concentration of these two, H plus COA minus divided by concentration of acetic acid. So this is called, K denotes the equilibrium constant. So this is basically acid base equilibria in water. So so then which law that describes this acid base equilibrium? So that is called Ostwald's dilution law. So relative strength of weak acids and weak base. So what is the relative strength? Weak acid, if it is weak acid is there and a weak base is there, so from the Westwald dilution law we can find out Ka, which the dissociation constant equal to alpha square C divided by 1 minus alpha. Alpha is degree of dissociation. So then ionic product. Ionic product means dissociation of water. Water plus water gives you H3O plus plus OH minus. Applying law of mass action to the above equation on a particular temperature, Ki equal to H plus into OH minus divided by H2O. Okay, so then ionic product of water equal to Kw, which is equal to Ki into concentration of water, which is equal to H plus ion concentration into OH minus ion concentration, which is called Kw, ionic product of water, which is equal to 10 to the power 1 into 10 to the power minus 14. So when the Kw equal to 1 into 10 to the power minus 14, so then So H plus ion concentration, if you know the H plus ion concentration, then OH minus ion concentration can be obtained by dividing it into with the Kw or ionic product of water, Kw divided by OH minus. So then next is called concept is called pH and POH. What is pH? pH is basically negative logarithmic of particular hydrogen ion concentration, and POH is the negative logarithmic of hydroxyl ion concentration. So next is coming hydrolysis. pH and POH, we know the pH scale. This is pH scale. pH scale, if it is acidic, the pH becomes 0 to 7. 7 is neutral, and if it is basic, it becomes 7 to 14. So it's basic, neutral, alkaline, acidic, basic. So next term is hydrolysis. Hydrolysis is basically, what is hydrolysis? The term hydrolysis derived from ancient word hydrolysis, breakdown. So it means dilution or destruction by water. Hydrolysis is a type of chemical reaction in which chemical bonds of a substance are decomposed by addition of water molecules. Okay, basically if a water molecule is added, so that then a particular molecule is decomposed by that process is called hydrolysis. Degree of hydrolysis is there. See, CH3CO minus plus water, CH3. So basically salt of a weak acid and a strong base. So that is degree of hydrolysis. So what is degree of hydrolysis? Is KH is called hydrolysis constant. With that hydrolysis constant, you can get it base into acid divided by unhydrolyzed salt. So next, salt of strong acid and weak base. So the salt of this category produces acidic solution on hydrolysis, as cationic part of the salt participates actively in hydrolysis and forms weak base which ionizes poorly. Therefore, concentration of hydrogen ions increases and solution exhibits acidic nature. So salt of strong acid, weak base, and then another thing is called salt of so first is degree of hydrolysis, case 1, and second is salt of strong acid and weak base. So then third is salt of weak acid and weak base. Okay, and then fourth, so this is how the different scenarios are there. What will happen? A strong acid will and weak base will react. What will happen? And a strong base, strong acid will be reacting. So what will happen? So the four different scenarios are there. You can go through them. We have very short period of time. Within 2 hours of time, we have to cover 110 pages. So that means it's too much to discuss. Just I'm just explaining you little bit, as little as possible. You read it yourself, and if you find it difficulty, you can ask later on. It's not a matter. But and you can talk to your RC center that, hey, yes, we have some difficulty here. They might arrange some other classes or something they can make for you. So but now I'm just buffer solution. Another important concept is buffer. A particular pH is required for a proper functioning of various chemicals, pharmaceuticals, biological, biotechnological process. Therefore, we need to have such solutions whose pH doesn't change appreciably. So basically, if a solution is there whose pH remains constant by addition of acid or base, that is called buffer solution. That means its pH is a constant. Buffer solutions, their pH is constant whether you add base to that or acid to that. If the buffer solution has a pH equal to 7, if you add base to that, that will remain 7. If you add acid to that, that will also remain 7. But to a certain extent, that is called buffer capacity. If you exceed the buffer capacity, so that means the absorbing power of the buffer solution, then your pH might change. But until the buffer capacity, if you add acid or base, that will not change. The pH will not change. So case 1, how a buffer is made: a mixture of weak acid and its salt, a mixture of weak base and its salt. So calculation of pH, you can calculate the pH of a buffer solution by buffer capacity. I told buffer capacity. The capacity of a buffer to withstand the change in pH is known as buffer capacity. A buffer solution that contains equivalent concentration of acid or base and its salt exhibit maximum buffer capacity. So common ion effect: if a strong electrolyte is introduced to a solution of feebly dissociated electrolyte that has that has at least an ion common with strong electrolyte, suppression of the in the ionization of weak electrolyte is observed. So basically, if a strong electrolyte is introduced to a solution of feebly dissociated electrolyte that has at least an ion common with the strong electrolyte. So if there is a common ion between a strong electrolyte and weak electrolyte, the suppression in the ionization of weak electrolyte is observed, and this phenomenon is known as common ion effect. So we go through them. Next is oxidation and reduction. So oxidation and reduction are two fundamental terms have been used in chemistry since beginning. Oxidation includes gain of oxygen, loss of hydrogen or electron, and increase in oxidation number or positive charge, whereas reduction deals with the loss of oxygen, gain of oxygen and gain of hydrogen, and decrease in oxidation number or positive charge or increase in negative charge of any atom or molecules or species. Okay, so oxidation, when ethane is oxidized, it gives you ethanol. So when ethanol is there, it is oxidized, it gives you aldehyde, loss of hydrogen. So Ag gives you Ag plus electron, loss of electron. So these are oxidation process. Reduction process, a loss of oxygen. So there are two oxygens are there in acetic acid, acetaldehyde is forming, loss of oxygen. So similarly, gain of electron or addition of hydrogen, that also reduction. So you go through them. A redox process is a very important process in an environment. So you should go through these oxidation reduction processes. So in unit 3, environmental chemistry 3. In environmental chemistry 3, we have what are the points discussed here? So it has like in environmental chemistry 3, so you have solubility and solubility product, solubility of gases, carbonate system, chemical speciation, chemistry of heavy metals, radionuclides, saturated and unsaturated hydrocarbons, chemistry of fuels, lubricants, biogas. So these are there. So then what is solubility and solubility product? Solubility product of a saturated solution of a sparingly soluble salt in water can be defined as the product of concentration of ions raised to the power equal to number of times ions occur in the equation representing the dissociation of electrolyte. When a saturated solution of an electrolyte is formed, a dynamic equilibrium is maintained between the excess of the solute and ions furnished by already dissolved electrolyte. So basically you see ax into by that equilibrate into ax to the power a plus ay into y b to the power x. According to the law of chemical equilibrium, equilibrium constant can be expressed as k equal to a into x ay into a into y bx. So divided by a into ax by, where axy, abx and axbi denote the activities of furnished ions a plus b minus and the undissolved electrolyte ax and by respectively. Now the activity of solid is taken by one as one by convention. Therefore, the equation can be represented as this. Ksp is known as solubility product and electrolyte. Okay, so this. So you just go through them. Then solubility of gases. Solubility of gases in water is governed by Henry laws. So what is the law? Henry's law. Henry's law governs the solubility of gases. This law states that solubility of a gas at constant temperature is directly proportional to the partial pressure of the gas gas in contact with the liquid. So a gaseous dissolves in liquid aqueous process A aqueous, where A aqueous is aqueous concentration of gases in moles per liter. Okay, Px is partial pressure of the gas in atmosphere. K is the Henry constant. So then here K equal to mole into liter inverse in atmosphere inverse. So next is the carbonate system. Carbonate system is the major portion of carbon is present in the ocean in the form of carbonate. So carbon is present as a carbonate. The carbonate system is primarily responsible for controlling the pH and regulates various biological processes, biogeochemical processes occurring in ocean. Carbon dioxide emitted through natural and anthropogenic sources are taken up by the oceans because it's converted to carbonates. This results in limiting the increase in carbon dioxide concentration and greenhouse warming, but increasing acidification of seawater. Rapid exchange of carbon dioxide occurs between the atmosphere and aquatic system through equilibrium of carbon dioxide and dissolved carbon dioxide. So basically carbonate plays an important role. Basically carbon dioxide in the atmosphere converted to carbonates, and that is stored in river bed, or ocean bed. So that's how that's the fate of carbon dioxide. Finally, ultimately, it converted to carbonate, but it's a very slow process. That's why, and it can prevent the formation of carbonate can prevent greenhouse effect of the carbon dioxide, but it's a very slow process. We are producing anthropogenic activities, producing carbon dioxide in an alarming rate, so which cannot be compensated by this carbonate formation. So that means we are producing carbon dioxide in a too higher rate than our planet can sustain it. So that means carbon dioxide level will automatically increase by anthropogenic activities that will lead to global warming. Okay, so that's why this is you go through them. What is that? So then chemical speciation. The term chemical speciation refers to specific chemical form of elements which may be inorganic, organic, or organometallic species in the environment. It also refers to oxidation state in which a particular element exists in the environment. Metals are non-biodegradable in nature. When they enter in the environment, they get partitioned into various physicochemical forms such as colloidal, chelated, and free ionic combined with other chemical forms. So chemical speciation means we should differentiate physical properties of physical properties and chemical behavior vary amongst the different species in the environment. So basically species to species it varies. Different oxidation state has a different biological function. Okay, so that's why chemical species, that is called arsenic, is extremely toxic in inorganic form, but arsenobetaine is non-toxic. So basically mercury is non-toxic, but alkyl mercury is highly toxic. So basically the mercury the toxicity varies from one to other. So the same chemical or same metal in a different form will be toxic, but in the other form it will be non-toxic. So the toxicity and mobility of metal ion depends upon concentration of metal ions, which decreases on complexation. So redox chemistry of heavy metals. So next is heavy metals. The term heavy metal refers to those elements which have density greater than 6 gram per cubic centimeter. Heavy metal they are heavy metal because their density is higher than 6 gram per cubic centimeter. Heavy metal occur in natural oils, sediments, deposits, and other water bodies. So because of their density, high density, they are called. So the heavy metals exert their toxic action by binding to active sites of the enzyme, thereby inhibiting the enzymatic action. They they have strong affinity for the sulfidyl groups and of the enzyme. Certain enzymes contain metal ions in their structures called metalloenzymes. So their action is inhibited when the essential metal ion of the enzyme is replaced by the toxic metal ion having same size or charge. Example, substitution of zinc by cadmium or zinc 2 plus containing metallozymes like carbonic anhydrase, carboxypeptidase, alcohol dehydrogenase. So basically these are some of the metallozymes where which are prone to the heavy metal toxicity. So see there are sulfur groups are there, heavy metal is there, they bind to that. So that means toxicity. This is how the heavy metal imparts its toxicity. What are the important cadmium? Cadmium is basically itai disease, responsible for itai disease. Arsenic is very toxic, causes keratose, skin discoloring, and leads to cancer, damage liver and kidney. So arsenic is very important. Lead it is basically it's a very extremely toxic element of heavy metal. So it has biologically very toxic effect. It shows very toxic effects, led to kidney malfunction, increased blood pressure, interference with vitamin D metabolism. So many other dangerous health effects are there. So lead, mercury is also very toxic element. Mercury, even if mercury metal is not toxic, it's chlorides, the mercury chloride, other organometallic sulfides, mercury sulfides, they are highly toxic to human health. So Ag non-toxic but vapors are inhaled are toxic. Ag2 plus not very soluble but low toxic. Ag2 plus toxic but not transported as biological tissues. Methyl mercury highly toxic. Dimethyl mercury low toxicity but easily transformed to methyl mercury. So then so these are heavy metal. So next is radionuclides. Radionuclides are the species of atom that emit radiation when they undergo radioactive decay through emission of alpha particles, beta particles, and gamma rays. Table provides the characteristic of defined decay processes. Alpha is +2 charge, beta is -1 charge, gamma no charge is zero, but no, but you see but alpha particle is the heaviest particle, beta is the least energetic is alpha particle, most energetic is gamma particle. So then when alpha and beta particles are emitted, the identity of element is changed. So but because it eliminates one of the negative charge beta particle, and alpha eliminates two positive charges. So basically you see U 238 by 92. 92 uranium, 92 is the atomic number, 238 is atomic mass. When it dissociates and a helium 42 nucleus goes out as alpha particle, then it's converted to thorium 90 234. So that means the decay of uranium 238 results thorium 234. In contrast to the emission, beta decay results in increasing atomic number by 1. So see, say carbon 14 6 when dissociates it or decays beta particle, that becomes nitrogen 14 7 and electron 0 1. So gamma rays are highly energetic electromagnetic radiations similar to X-rays having no charge mass. Okay, so the next is saturated and unsaturated hydrocarbons. Majority of hydrocarbons have their widespread use in fuels and therefore represents the most important organic pollutant of the atmosphere. The anthropogenic sources of hydrocarbon pollutant encountered in atmosphere comes from incomplete combustion of gasoline. Hydrocarbons are broadly classified as saturated hydrocarbons, unsaturated hydrocarbons. Saturated hydrocarbon means there is no double bonds or triple bonds are there. Unsaturated, they have alkenes, alkynes, they have double and triple bonds are there. Carbon carbon double bond, triple bonds. But in the general formula, CnH2n is the alkane, alkane, cyclic alkane CN. So acetylene is there, 1 butane is there, benzene is there, 2,6-dimethyl naphthalene is there, pyrene is there. So these are aromatic and this is aliphatic. So this is alkyne, this is alkyne. So unsaturated, this is also unsaturated. Saturated, the structural different type of hydrocarbons, pollutants. These are pollutants, aromatic hydrocarbons and aliphatic. So this is aliphatic and unsaturated hydrocarbons. So these are pollutants in the. So next is chemistry of fuel. Chemistry of fuel. Fuel means what? Our petroleum that we use in our vehicles or for other activities where we get energy. That is also called as gasoline. The first product in distillation of crude oil is gasoline. Generally, the boiling range of gasoline between 25 to 150 degrees centigrade. Gasoline are sometimes classified as motor gasoline for use in automobiles and light truck, aviation gasoline for use in piston engine aircrafts. Uh, um, Hydrocarbons having 3 to 8 carbons condensed from natural gas are composed of natural gasoline. Natural gasoline does not provide good combustion performance desirable for automobile engine. Consequently, it is now used mainly as feedstock for petrochemical industry. So this is called gasoline, basically petroleum product. It is called gasoline. So octane number of various hydrocarbons. You see, hydrocarbons are basically gasoline is a mixture of number of hydrocarbons, n-butane, n-pentane, n-hexane. So these are number of. So there is octane number means how much energy they produced. Higher the octane number, higher the energy they produce. So n-butane, which like the smaller the hydrocarbon, the higher is the octane number. As the size increases, their octane number gradually decreases, but there's slight variation. But here see, trimethyl pentane is there. It's a branched alkene. Its octane number is very high. So but generally, if a branched alkane is formed, it's branching occur. More is the branching in the hydrocarbon, more will be the octane number. So this is how. And then aromatic amines have more higher octane numbers. That means benzene, toluene, xylene, paraxylene. So they have more higher octane number. Octane number can be increased by 3 ways. Octane number means, as I told, if the higher the octane number, higher is the energy generated by burning that particular hydrocarbon. So octane number, how can you increase? By cracking, catalytic reforming, anti-knocking compounds, octane boosters, all those. Chemistry of gasoline fuel additives. Chemistry of gasoline fuel additives. The fuel additives in very small doses are added to enhance the performance of the fuel, which otherwise cannot be obtained through refining process. Reason for using additives in fuel include reduction in emission from combustion of fuel, improve combustion properties of fuel, provide cleanliness and protection to engine, increase stability of fuel. So So basically, there are six type of gasoline fuel additives: antioxidants, metal deactivators, octane boosters, anti-icing activity additives, combustion improvers, deposit control additives, detergent dispersants. So the first is anti-knocking agents. Knocking is in the internal combustion engine affect the efficiency of the vehicle. So basically, knocking means, so if in a combustion engine in your vehicle, if you add an anti-knocking agent, that will increase the combustion efficiency of the particular vehicle. It can be minimized by engine design and adjusting operating condition, or by using high octane gasoline. So this is called anti-knocking agents. So what are the examples? MMT, methyl cyclopentadienyl manganese tricarbonyl, MMT. So this is the structure of MMT. So here manganese and iron are there. So next is lubricants. What is lubricant? You know, grease is used as lubricant. That means that reduces the friction. Lubricant is a substance which is introduced between two sliding surfaces to reduce friction and wear rate. This process of reducing friction by application of lubricant is referred to as lubrication. Function of lubricants: reduces friction and wear and tear of surfaces, acts as a coolant by dissipating heat, prevent entry of moisture, all this, minimizes power loss in internal combustion engine, reduces maintenance costs. So mechanism, how the what is the mechanism of lubrication? Thick film lubrication or hydrodynamic lubrication, thin film or boundary lubrication, extreme pressure lubrication. Classification of lubricants: lubricating oils or liquid lubricants, greases or semi-solid lubricants, solid lubricants. So there are different types: lubricating oils, grease, solid lubricants. Okay, so you go through them. So you have a classification of solid lubricants, advantages, disadvantages of solid lubricants, classification of one of the important solid lubricant is graphite. Graphite is most commonly used as solid lubricant in powder or suspension. Graphite, if you know the powder graphite, if you add, it will act as a solid lubricant and reduce the friction between two surfaces. Okay. Properties of lubricants. What are the properties of lubricants? Viscosity. Viscosity means it is defined as the resistance offered due to the motion of the forces between the fluid molecules. Corrosion stability. Steel or copper corrosion tests are carried out to estimate the corrosive stability of lubricant. Uh, Flash point and fire point. Okay, then aniline point. So then cloud point and pour point. So these are different parameters by which you can describe, or you can show the properties or compare the properties of different lubricants. So next is biogas. Increasing production of organic waste is one of the major environmental concerns present in the scenario. Sustainable waste management as well as waste prevention. Am I audible to all of you?
Yes, sir.
Yes, sir.
So gradually you are reducing, your number is reducing, right?
Yes, sir.
Biogas. Increasing production of organic waste in one of the major environmental concerns. So basically organic waste is generated, means like food waste all kind of waste, organic waste, or the fruits waste, fruit or food material. So anything that can be easily composted, it easily undergo putrefied waste. It's like putrefaction, like easily it can be wasted. Food, or 1 or 2 days if you keep, it will be wasted. So that is called organic waste. So sustainable waste management as well as waste prevention has become major goal, has have become major goals to reduce pollution and greenhouse gas emission to mitigate global climate change. So basically, how by you can manage such organic wastes by make compost, or you can do the what is called anaerobic digestion of these waste, organic waste, to produce biogas. So what it is, uncontrolled waste dumping or incineration of organic waste are nowadays not recommended practices for waste disposal. This problem can be circumvented by production of biogas by degrading biological waste in the presence of anaerobic bacteria. So basically, anaerobic digestion of the organic waste in the presence of anaerobic bacteria generates methane. Okay, so that methane and carbon dioxide. So this methane is a biogas called biogas, which is used for burning, cooking, and also for energy, just for energy, because methane can be burned to provide energy. So that is called biogas. So the biogas is a combustible gas chiefly comprising of methane 50 to 70%, carbon dioxide 25 to 30% as a primary constituent. Other could be hydrogen, nitrogen, hydrogen sulfide, and oxygen. Examples of biogas include natural gas produced by decaying animals and vegetable waste buried under the earth's surface. Gobar gas plant, that is also anaerobic fermentation of cattle dung. Sewage gas produced from municipal solid waste, including human and animal feces. Gobar gas. So with this, we are done with this part. And then finally, developments in environmental chemistry. So need of, what are those need of emergence of green chemistry, Bhopal gas tragedy, thalidomide disaster, Times Beach, Love Canal disaster. So these are evolution of green chemistry to reduce pollution, or polluting pollution generating processes. Okay, so some important laws for environmental protection, green chemistry and sustainability, concept of green chemistry, greener solvents, and earth friendly plastics, environmentally benign pesticides. So all these things are included in there. Basically, green evolution of green chemistry to prevent the generation of pollutants. Okay, that is called this need for emergence of green chemistry. We environmental chemistry and green chemistry are completely different. As I told previously, environmental chemistry is the chemistry of the pollutants, whereas the green chemistry is the chemistry that deals with how to reduce the generation of pollutants. That those are fundamentally different. So because of the non emergence of the green chemistry, or when the green chemistry was not practiced, because of that the harmful chemicals, that phosgene gas was the cause of the Bhopal gas tragedy. More than 30,000, 40,000 people died because of phosgene gas that come out. Thalidomide disaster, it is also thalidomide is a drug that was given to the people, but it has some other potential harmful effects on the body. So these happened because of the we were using some chemicals or chemical processes in those particular cases, which those are harmful to human beings. So that means to how to reduce those harmful chemicals, the use or generation of those harmful chemicals by using green chemistry principles. So that is Some important laws of environmental protection. What are the important laws of environmental protection? How to protect? 1970 National Environmental Policy Act, NEPA. 1970 Clean Air Act. 1972 Pesticide Control Act. 1972 Clean Water Act. 1976 Toxic Substances Control Act. So then green chemistry and sustainability. In 1990, the Environmental Protection Energy Agency EPA came in the first act called Pollution Prevention Act. So this is in 1990. Another act was enacted that is called Pollution Prevention. So green chemistry and sustainability is for pollution prevention. Okay, so that is focused on pollution prevention at the source, which in turn led to emergence of green chemistry. This act states pollution prevention is reducing or eliminating waste at the source by modifying the production process, promoting the use of non-toxic and less toxic substances. So basically, when we are producing a method, industrial method of producing chemicals, we should prevent the process, the generation of harmful substances and the use of harmful substances. So that is called green chemistry. So what is the green chemistry is central to sustainable development, or it can help in accomplishing sustainability. Okay, so as per the United Nations Commission on Sustainable Development, so its sustainable development is defined as meeting the needs of the present without compromising the ability of future generation to meet their own needs. So basically, our future, we should think about our future generations. Maybe after 100 years, what will happen to them? If when there will be no fossil fuel, so when there will be no coal available for them, so how they will sustain their life? So if we think about that, that is called sustainable development. So that means thinking for the future generations. So concept of green chemistry, the term green is often associated with natural surroundings. Okay, so as per EPA, green chemistry prevents. As per EPA, green chemistry prevents pollution at the molecular level. In its philosophy that applies to all areas of chemistry, we cannot define it as a new branch of chemistry, but it is the way of chemistry should be practiced. That is dealing with chemical and their manufacturing processes to minimize any negative environment effects. Okay, so basically that is the approach of green chemistry: waste, how to reduce waste, materials, energy, hazard, risk, and cost. So this is green chemistry. So reduce everything: waste generation, materials use, energy use, less hazardous, reduce risk and cost. So this is, there are 12 principles of green chemistry. So what are those? First is prevent waste. Second is atom economy. Third is designing less hazardous chemical synthesis. Fourth, designing safer products. Fifth, safer solvents and auxiliaries. Sixth, design of energy efficiency. Seventh, renewable resources. Eight, reduce derivatives. 9, use of selective catalyst. 10, design for degradation. 11, real-time analysis for pollution prevention. 12, inherently safer chemistry for accident prevention. So basically, there are 12 principles. Those are adopted and called as 12 principles of green chemistry that can reduce the use of harmful chemicals and generation of harmful chemicals, and that can also help us achieve sustainability. That means the while practicing this green chemistry, we always think about sustainable development. That means what our future generation will do when the when one of the principles there is a renewable. So always use the renewable resources. That means which the resources which are renewable can be renewed. Non-renewable resources, what is non-renewable resource? Like petroleum products coming from fossil fuel, that is non-renewable. Once it is depleted, means depleted, we cannot regenerate it. So same thing. But if you use wind energy, if you use what solar energy, so that is renewable. So next is greener solvents. So what is a greener solvent? Solvents have attracted a great deal of attention in scientific community, owing to crucial role they play in agrochemicals, pharmaceuticals, paints, household and industrial cleaners, etc. Not only do they provide a medium for the dissociation of wide variety of substances, but also accelerate accelerate many of the reactions. The largest user of solvents is the pharmaceutical sector. Issues with the use of traditional solvents. What is the issue with why we use green solvent? Because there are several issues with traditional solvents like chlorinated organics, aromatic organics, aromatic compounds like benzene. So then um, so there are many issues like low toxicity. So what is the properties of green solvents? They have low toxicity, convenient accessibility, greater efficiency, enhanced reusability, and increased biodegradability. So these are the five things that the green solvent possesses, whereas these things are not found in conventional solvents. Alternative green solvents, what are the examples? Like water. Water is a solvent we are drinking, it's non-toxic completely. Many reaction can be done in water medium or water supercritical fluids, supercritical carbon dioxide. That is called supercritical fluids. And then next, ionic liquids, liquid polymers, bio-based renewable solvents. So all this. Next is earth-friendly plastics. What is earth-friendly plastics? That means that those are biodegradable plastics. Any plastic like your polythenes that you use, that is not biodegradable. So that means it is not earth-friendly plastics. Earth-friendly plastics means something which is biodegradable. Plastics. So see polyethylene PET polymer used for water bottles, containers, biscuit trays, all those. Next, high density polyethylene HDPE. So shampoo bottles, milk bottles, freezer bags, all those HDPE. LDPE bags, trays, container, food packaging. So polystyrene, polypropylene. So they have a lot of industrial and household applications, but they are not biodegradable. So primary issues with the synthetic plastics, they are produced from non-renewable resource. First thing, they are produced from non-renewable petroleum resources, include crude oil, which are depleting. Most of the synthetic plastic require the use of destructive thermal treatment such as combustion or pyrolysis, which requires high temperature. Okay, so and green plastic. What is the greening of plastic? What is green plastic? Earth-friendly plastics or bioplastics commonly obtained from natural origin, such as plants, animals, and microorganisms, can be classified as green plastic. Greening of plastics like polyhydroxyalkanoids (PHAs), polylactic acids, cellulose-based plastics, lignin-based plastics. Green Chemistry Challenge Award for Innovation of PLA. So Nature of Work LLC received Greener Reaction Conditions Award for replacing petroleum-based polymer with bio-based compostable and recyclable polylactic acids. This PLA-based bioplastics is one of the most promising and popular materials as the alternative to synthetic polymer. So basically, many polymers which are now like recyclable polylactic acids, so they are biodegradable plastics. They can be used. Conversion of plastic waste into valuables. We can convert plastic waste into valuables. Environmentally benign plasticides. Over the last decades, the global agricultural sector has extensively relied on pesticides. So, and have undoubtedly increased the crop yield and reduced post-harvest losses. But unfortunately, their expanded use has polluted the environment while affecting human health considerably. As per estimates, barely zero point 0.1 of the total agrochemicals utilized in crop protection succumbs to reach the target pest, while the remaining 99.9% is undeniably bound to enter the environment, thus causing hazard to non-target organisms. Effect of synthetic pesticides on human health and environment. So what is the human health? Pesticide. So what is the human health? So they many of the pesticides they have very strong effect on our body, kidney, our liver, damage to kidney, liver, our entire system, and entire death. And it can also, high doses of pesticides can cause death of human beings. So next, environmentally benign pesticide. What is the environmentally benign pesticide? That can be easily biodegraded. Pesticides which can be easily biodegraded and less harmful to humans are called environmentally benign pesticides. Examples: microbial pesticides, plant pesticides, biochemical pesticides, soap-based insecticides, neem oil insecticides, diatomaceous earth, garlic insecticide spray, tomato leaf, all leaves. All these are all the biodegradable pesticides which can be used as green pesticides. Okay, with this, I think we are done with all the 4 units today. And next class we will discuss the second block, block 2, and the units are, there are 3 units in the block 2. That's what we will discuss. If you go through this part, the block 1 of this environmental chemistry, if you find any problem or difficulty, you can ask me in the next class. Okay, so for tomorrow, how many total number of students are there in your class?
Sir, we always joined through online. We don't know how much in the base total capacity base.
Okay, so you only these 10-15 students you join online.
From starting 20, maximum 20 people join class. Not more than 20, sir. Slowly decrease the number.
Okay. You can talk to them and tell them to join in more number of students should join. So I'm actually I'm spending a lot of time and also spending my energy. So if more students will join, it will be good. Okay. Thank you all. So we are almost. Any questions you want to ask? Any questions you want to ask?
No, sir.
So then
Hello,
should I
good evening,
leave?
sir. Hello.
Yes.
Sir, in Unit 1,
Uh-huh.
kinetics of reaction of different order, ଆମକୁ ସବୁ equation ଲେଖିବାକୁ ହେବ କି sir?
ହଁ ଲେଖିବାକୁ ପଡିବ, ପଚାରି ଲେଖିବ ନାହିଁ ତମେ ତାର ଇକ୍ୱେସନ, ରେଟ୍ ଇକ୍ୱେସନ ଲେଖିବ, ଆଉ
ଆଜ୍ଞା
ତାର ଅର୍ଡର କଣ, ତାର ମୋଲେକୁଲାରିଟି କଣ, ସେଗୁଡା ସବୁ ତ ଜାଣିବ ନା। ମୁଁ କହିଦେଲି, ଟିକେ କହିଦେଲି, ଯେହେତୁ ଏଟା ବହୁତ କମ
ଆଜ୍ଞା
ସମୟରେ ଆମେ ଏତେ ଗୁଡାଏ ପେଜ ପଢିଲେ, ସୋ वी कुड नॉट फिनिश इट कम्प्लीटली, ମାନେ ଭଲ ଭାବେ ଆମେ ତ ପଢି ପାରିଲେନି। ତେଣୁକରି
ଆଜ୍ଞା
ତମେ ନିଜେ ନିଜେ ଯଦି ପଢିବ, ପ୍ରାକ୍ଟିସ କରିବ, ତାହେଲେ ତମେ ଜାଣିପାରିବ ଜିନିଷ ଗୁଡା କଣ ଅଛି ସେଥିରେ।
ସାର୍ ଆଉ ଗୋଟେ ସେ ଯୋଉ
ଆଉ କୁହ କଣ ହେଲା?
ସାର୍ adsorption catalyst ରେ ସାର୍ ଆଇସୋଥର୍ମ ଇକ୍ୱେସନ ସବୁ ଲେଖିବାକୁ ହେବ ସାର୍ ଆମ ଏକ୍ସାମ
ହଁ
ଟର୍ମ
ଲେଖିବନି,
ରେ ଯୋଉ
ସେଟା
କ୍ୱେଶ୍ଚନ
ଆଇସୋଥର୍ମ
ଅଛି।
ଆଇସୋଥର୍ମ ଇକ୍ୱେସନ, ସେଥିରେ 6-7ଟା ଆଇସୋଥର୍ମ ଇକ୍ୱେସନ ଅଛି। Based
ଆଜ୍ଞା
on
ଆଜ୍ଞା
those isotherm equations, that is the
ଆଜ୍ଞା
basic principle. If your adsorption process is governed by that adsorption isotherms, okay, different adsorbents, they follow different adsorption isotherm, ବୁଝିପାରିଲ ତ? ଗୋଟେ adsorbent ଯଦି ଗୋଟେ isotherm follow କଲା, other adsorbent might follow the other adsorption isotherm. ସେଥିପାଇଁ କି you have to you should know the different types of adsorption isotherms.
ସାର୍
And
ଆମର ଟର୍ମ ଆଣ୍ଡ ଏକ୍ସାମ ରେ କ୍ୱେଶ୍ଚନ ଆସିଲେ ଆମର ସାର୍ ସେ ଆଇସୋଥର୍ମ ଇକ୍ୱେସନ ସବୁ ଲେଖିବାକୁ ପଡିବ ସାର୍?
ଲେଖିବାକୁ ପଡିବ। ଯଦି ତମର କ୍ୱେଶ୍ଚିନ୍ ଆସିଥିବ ପର୍ଟିକୁଲାର, ଯଦି କଣ କଣ adsorption isotherm ଥିବ, ତାହେଲେ ଲେଖିବାକୁ ପଡିବ ଇକ୍ୱେସନ।
ଆଜ୍ଞା ସାର୍,
ଯଦି
ଥ୍ୟାଙ୍କ ୟୁ ସାର୍,
ଆଇସୋଥର୍ମ ଉପରେ ଆସିଥିବ ଆନ୍ସର କ୍ୱେଶ୍ଚିନ୍।
ଥ୍ୟାଙ୍କ ୟୁ ସାର୍।
Any more question? Okay, thank you all again for joining. See you tomorrow.
Okay, sir.
Thank you, sir.